Okay. So in the previous class, we discussed about the system modeling elements. So we discussed two elements. One is for electrical and another is for mechanical. Now to start this lecture with, we'll be discussing about the electrical and mechanical analogies. That means the similarity between the electrical system modeling elements and the mechanical system modeling elements. So there we were having this mass spring element and as well as the dashboard system. So I told you that the spring and the mass stores the energy. Mass stores the energy in the form of half mv square. Spring stores the energy in the form of half kx square, while the dashboard dissipates the energy. So we try to formulate that in the form of a power for dissipation. The same thing was with the electrical system. Now, if we are comparing the two systems, the electrical system as well as the mechanical system, we'll try to create analogies between the two. Over here, if you see, this is the diagram, which completely itself explains everything. In the left-hand side, we have a mass, dashboard, and a spring system. And over here, we are having the resistance, inductor, and the applied voltage, and current is flowing through this because we have applied a potential difference also. Okay, looking at this, the potential difference, the current is being analogous to the force. As we apply force, there is a motion or there is a displacement. Similarly, whenever there is a current flowing in the system, then we can say there is a potential difference is created across 2 points. And so potential difference is analogous to the velocity. And the dashboard constant C to the reciprocal of the resistance. So over here, your resistance is working as a dashboard. So it will be dissipating the energy over here. So this was the equation we have driven for the mass system. That was, we were having a mass system, inertia system, spring system, and the dashboard system, so which was equivalent to the force applied. Over here we have a similar analogy for the electrical system. These were the elements we have driven on that day, which were equivalent to the mass, to the spring, and to the dashboard. So that is equal to the voltage over here. Now the third element which we need to discuss before going for the system modeling in the next chapter of W. Bolton book. At this time, I'm again telling you that you should have that book with you, because whole of your syllabus of Mechatronics has been made from the W. Bolton book only. So try to read that book. Okay. So this time only I'm also teaching you from the W. Bolton book only. So over here we are discussing the fluid flow system. So there are basically 3 basic building blocks which can be considered to be equivalent of electrical resistance, capacitance, and inductance. So, okay, so that means whenever we are trying to model a system, we always look for the 3 systems. There is a mass, the spring system, and the dashboard. That will be same for every kind of a system modeling, whether we are doing it for electrical, for a fluid system, or whether we are doing for the thermal system, which we'll be discussing today only. So fluid system can be considered to fall into 2 categories: hydraulic, where the fluid is a liquid and is deemed to be incompressible, and pneumatic, where it is a gas which can be compressed and consequently shows a density change. So that is the difference with this fluid system as compared to the other previous system that we have discussed, like mass system, the electrical system. So this fluid system is somewhat different, because over here the fluid behaves differently when it's a fluid, or if fluid is a liquid, or whether when it is a gas. So we'll be discussing that when we going through this topic of fluid system building blocks. So first of all, the first element is nothing but the hydraulic resistance. It is the resistance to flow which occurs as a result of liquid flowing through valves or changes in a pipe diameter. So basically, whenever we create a pressure difference at 2 ends, it will make your liquid to flow from one end to another end. Now, what kind of a resistance it takes during that motion, that gives the discharge at the other end. Suppose the resistance is high, then your discharge will be less at the output point. So that's why this equation has been made. P1 minus P2 is equal to R times Q. The relationship between the volume rate of flow of liquid Q through the resistance element and the resulting pressure difference P1 P2 is equal to P1 minus P2 is equal to R times Q, where R is a constant called the hydraulic resistance. The bigger the resistance, the bigger the pressure difference for a given rate of flow. This equation like that for the electrical resistance and Ohm's law assume a linear relationship that you can see over here. Such hydraulic linear resistance occurs with orderly flow of, that is okay completely. Then we come to the hydraulic capacitance. Now, the capacitance term is used to describe energy stored within a liquid, whether it is stored in the form of a potential energy. So whenever you are storing a liquid, it goes up to some height h, then always there is a storage of potential energy in the liquid, and that potential energy we will be taking this into terms of capacitance. For such a capacitance, the rate of change of volume in the container, that is dV by dt, is equal to the difference between the volumetric rate at which the liquid enters the container Q1 and the rate at which it leaves Q2. So Q1 minus Q2 is equal to rate of change of your volumetric rate. You can simply say this thing. But V is equal to what? Volume is equal to what? Area into height. So A is the cross-sectional area of the container and H is the height. So that means Q1 minus Q2 is equal to D. So we have put the value of V over here, which is area into height. So A is equal to dH by dt. But the pressure difference between the input and output is P, where P is equal to H rho G, that you know already know. Pressure is always equal to H rho G, where rho being the liquid density, G is the acceleration due to gravity. So we can replace this with the equal to P by rho G. Your H has been replaced over here with P by rho G. So taking rho and G as constant, taking out from the differentiation. So A by rho G into dP by dt is equal to your liquid discharge, that is rate of discharge of the liquid, Q1 minus Q2. So this term A by rho G, this term is now known as the capacitance. Okay, so thus Q1 minus Q2 is equal to C times dP by dt. Taking its integration, P is equal to 1 by C integration of Q1 minus Q2 into dt. Okay, so this is another element you must remember while you will be using this for the system modeling in the next chapter. Then comes your hydraulic inertance. It is the equivalent of inductance in electrical systems or a spring in a mechanical system. So we have got another element which is equivalent to the spring. You can switch off your mic if you want. That will be okay. So now hydraulic inertance is equivalent to the spring in the mechanical system. To accelerate a fluid and so increase its velocity, a force is required. As simple as that. Consider a block of liquid of mass m. The net force acting on the liquid is F1 minus F2 is equal to P1A minus P2A. It is equal to P1 minus P2 times A. Okay. So that's a simple formula. You all already know that pressure into area is equal to the force applied. So we'll be using that over here only, where P1 minus P2 is the pressure difference and A is the cross-sectional area. So what will be this is going to give us the force. So P1 minus P2 into A is equal to mass into acceleration. What is acceleration? It is the rate of change of velocity. But the mass of liquid concern has a volume of what? Area into length, where L is the length of the block of liquid or the distance between the points in the liquid where the pressure P1 and P2 are measured. So that means this mass quantity, this quantity we have confined in that length only where we are measuring the pressure P1 and P2. So whatever the length is lying between these 2 points, P1 and P2, into the area of that vessel or container, that gives you the mass into the volume into density gives you the mass. Okay. So mass over here will be equal to area into length will be equal to the volume. L is the difference between the length between the 2 points. Area is the area of the container, and rho is the density. So we are replacing mass equivalent to area into length into rho into dV by dt. Okay, but the volume flow rate of liquid is what? Area into velocity. This must be clear to you. Okay, because volume flow rate is what? Area into length, that is volume, divided by time. Length upon time is what? Velocity. So that means Q is equal to area into velocity. So replacing these few terms, what we will be getting, P1 minus P2 into A is equal to L rho dq by dt. So we have replaced this V by A into V and cancelling out the common terms and everything. We will be getting this because over here V is equal to what? Q by A. So A was already means outside. So A will be cancelling out with A because A is a constant. So P1 minus P2 into A is equal to L times rho into dq by dt. Further, we are taking, please switch off your video. So P1 minus P2 into A is equal to L rho dq by dt, and further P1 minus P2 taking A over here. So what we get? L rho by A into dq by dt. What is L rho by A? This term is now known as a inductance. Okay. So earlier you have defined the capacitance. Capacitance was A by rho into G. Now you have defined inductance, which is equal to L rho by A. Okay. So you must remember these elements. With the pneumatic system, the three basic building blocks are, now we have just discussed the system with a fluid as equal to a liquid. Now we are entering into a pneumatic system where our fluid will be equal to a gas. Okay. So again, there will be three basic building blocks. One is the resistance, then there is a capacitance, then there is an inertance. However, gases differ from liquids. You all know, because gases are compressible. That is, a change in pressure causes a change in volume and hence density. Okay. So pneumatic resistance is defined in terms of mass flow rate of flow dm by dt. Okay. So this is often written as m with a dot above it. You can simply means this one. So instead of writing dm by dt, you can write m dot. That entirely depends upon you. It's just a representation. So in the previous, while we were having a liquid, this was the equation. P1 minus P2 is equal to R times Q. Now, because the gases are compressible, this equation have been changed into P1 minus P2 is equal to R times M dot. The next next thing is to calculate the capacitance. C is due to the compressibility of the gas and is comparable with the way in which the compression of a spring stores energy. Earlier, while we were discussing about the liquid, then we have taken the height of the liquid as our potential energy. Now over here, because the gases are compressible, so once they get the compression, so it is a similar case of a spring where spring gets compressed and stores the energy. So if there is a mass flow rate equal to dm1 by dt entering a container and mass flow rate of dm2 by dt leaving the container, then the rate at which the mass in the container is changing is what? dm1 by dt minus dm2 by dt, because the gases are compressible. So in case of liquid, what was that? In case of liquid, क्या था कि जितना mass enter कर रहा था उतना leave कर रहा था in a given time. But over here, because gases are compressible, so that means if M1 is entering the system and M2 is leaving the system, then there is a change in the mass flow rates, which will be equal to dm1 by dt minus dm2 by dt. If the gas in the container has a density rho, then the rate of change of mass in the container would be what? Rate of change of mass would be equal to d rho v by dt. What is rho into v? It is nothing but mass. Now, because the gases are compressed, so both rho and v will vary with time. Okay. In earlier case, in case of liquid, only volume was varying with time. So we were calculating the volume flow rate or volumetric flow rate. But over here, because density is also changing in case of gas, so we cannot take out the density out of the differentiation because density is also variable over here. So therefore, rate of change of mass in container would be equal to rho dv by dt plus v rho d rho by dt. Okay. So this is what you are getting. Since dv by dt can be further written as a chain reaction like dv by d P into dP by dt, and for an ideal gas PV is equal to mRT, with consequently what is P? It is equal to m by VRT, and m by V is nothing but rho RT. So d rho by dt is equal to 1 by RT dP by, this is a simple differentiation equation, you all know about it. So rate of change of mass in container, by replacing all these quantities, what you will be getting, rho dB by dP into dP by dt plus V by rho T, RT into dP by dt. So this is a rate of change of mass in the container. Now the rate of change of mass of container, what was that? dm1 by dt minus dm2 by dt. Earlier I told you, so this must be equal to this. So the pneumatic capacitance due to the change in volume of the container, what was that? Rho dV by dP. And the pneumatic capacitance due to change in the because of the compressibility of the gas, that will be equal to V by RT. Okay? So we got two things over here, rho dV by dP. This is why, because of the change in volume. This is why, this is change of your this is because of your compressibility. So this is C1 and C2. So that means your variability in the mass flow rate will be equal to dm1 by dt minus dm2 by dt equals to C1 plus C2 into dP by dt. Further, taking integration, the terms on the left side and doing some integration, this is the another equation that you will be getting, which we have also driven for the liquid system. Okay, so you just need to remember these equations as well as the compare these equations. Okay. Next is pneumatic inertance. This is due to the pressure drop necessary to accelerate a block of gas, which is a similar definition which was for the liquid as well. Now, according to Newton's second law, the net force is ma, which is equal to m dmv by dt. Since the force is provided by the pressure difference P1 minus P2, then if A is the cross-sectional area of the block of gas being accelerated, then P1 minus P2 into area is equal to dmv by dt. But m, the mass of the gas being accelerated, equals to rho La, right? Where rho being the gas density, L is the length of the block, which we have also done for the liquid case. And the volume flow rate will be equal to area into velocity, which we already have done in liquid case. So mv is equal to rho La into Q by A, which is A cancels out with A. So what is mv? It is equal to rho L Q. And so P1 minus P2 into A is equal to L d rho Q by dt, but m dot is equal to what? Rho into Q. And so finally P1 minus P2 is equal to I dm dot by dt, and I being the inertance is equal to L by A. Okay. So these are some of the terms that you must remember. So over here, he has given you summary of all those equations for hydraulic system, inertance, the energy stored over here, the capacitance, the energy stored in the capacitance, the resistance. While I'm talking about resistance, there will not be any stored in the energy. So it will be the power dissipation. So over here, you can see this is the power dissipation. And then we talk about, this was the hydraulic system over here. Now this is what? This is the pneumatic system. So inertance is equal to m dot 1 by L, integration of this energy stored and capacitance and the resistance. So these elements are very, very important for building a system later on. Okay. Next. Now we'll be taking one example over here. We'll be considering a fluid system. We'll try to apply these elements over here. Okay. So first of all, building up a model for a fluid system. This is the next topic. It figure shows a simple, this figure shows a, this one shows you a simple system. It shows a simple hydraulic system, a liquid entering and leaving a container. Such a system can be considered to consist of a capacitor, the liquid in the container with a resistor, the valve. Okay, so all those things, the valve, whatever the opening of the valve is, that will decrease the resistance for the system, and it will increase the flow rate of the liquid from the container. Okay, so valve will be acting as a resistance over here, and the liquid which is inside the container, the height of that will give that will be equal to the capacitance of the system. Now, Inertance can be neglected since flow rate changes only very slowly. For the capacitor, we can write, already we have driven this formula, Q1 minus Q2 is equal to C dP by dt. We are considering a liquid case only. So the rate at which the liquid leaves the container is Q2. This equation has earlier been driven. You must remember that for a liquid system, P1 minus P2 is equal to RQ2. The pressure difference is the pressure due to the height of the liquid in the container, thus H rho g, all those things we already have done. And since C is equal to A by rho g, we have given this formula. So we're using all those formulas, what we get, Q1 is equal to A dH by dt plus rho g H by R. This equation describes how the height of the liquid in the container depends on the rate of input of liquid into the container. Okay. Next is a bellow. There is a resistance, construction resistance, and then this is how this is for a pneumatic system. So this air has been blown over here. So m dot is the mass, which mass is the mass flow rate of the air into the bellow. So bellow is an example of simple pneumatic system. Resistance is provided by constriction, which restricts the rate of flow of gas into the bellows, and capacitance is provided by the bellow itself. Okay. So the amount of the mass flow rate inside the bellow will give you the capacitance. Inertance again can be neglected because the flow rate changes very slowly. So now we'll be using the equations for the pneumatic system. So P1 minus P2 was equal to R into m dot. It was earlier was equal to R into Q. For a pneumatic system, it is now m dot. So this equation already we have driven, m1 dot minus m2 dot is equal to C1 plus C2. This C1 is for the volume change and this is for the compressibility. So dP2 by dt. So this is the equation we already have driven. Now P1 minus P2 by R is equal to C1 plus C2 dP by dt. So hence finally we will be getting this equation. Please switch off your mic. Who is there? Gautam, please switch off your mic, beta. Okay, so P1 is equal to R times C1 plus C2 into dP2 by dt plus P2. This equation describes how the pressure in the bellows P2 varies with time when there is an input of a pressure P1. Okay. So this equation describes the bellows expand or contracts as a result of the pressure change. Inside it, bellow are just a form of a spring, and so we can write F is equal to Kx for a bellow. Whenever you push some gas into the bellow, it will expand, otherwise it will compress. So bellow is nothing but a similar analogies to the spring. For the relationship between the force F causing an expansion or contraction and the resulting displacement X, where K is the spring constant for bellows. But the force F depends upon the pressure P2, with P2 is equal to F by A, where A is the cross-section area of the bellows. Thus P2 into A is equal to F, F is equal to Kx. So we got this another equation, hence substituting for P2 we already have driven in the previous equation over here. So we'll be using that P2, we'll be using over here. So P1 is equal to R times C1 plus C2 K by A dx by. This is another equation that you can get. This equation is a first order differential equation. Describes how the extension or contraction X of the bellows changes with time when there is an input of a pressure P1. Okay. Okay. Still we have time, 10 minutes. So the pneumatic capacitance due to the change in the volume of the container C1 is equal to rho dV by dP2. And since volume is equal to A times displacement, so C1 is equal to, replacing the V over in this equation, we will get rho A dx by dP2. So we have just replaced the value of V into this equation. But for the bellows, P2 into A is equal to Kx, which already we have given over here. So finally C1 is equal to rho into A dx by d Kx by A. So this is the value for C1. C to the pneumatic capacitance due to the compressibility of the air is V by RT is equal to AX by RT. The following illustrates how for the hydraulic system shown in figure relationships. This one, okay. This is the system I was talking about. So a Q1 is enter over here, then there is a wall which is causing a resistance, and yes. So through this resistance, the liquid enters into the second container, and finally it leaves through this another wall which is R2, and finally you will get the discharge Q3 over here. So you get Q1 as a liquid flow rate which is entering into the system, then Q2 is leaving the first system, Q2 is entering into the second system, and Q3 is leaving the second system. Okay. So Q1 minus Q2, which we already have done. This is for the first system, the capacitor. Q1 minus Q2 is C1 dP by dt. Again, this is a liquid system, so you need not to worry about the mass flow rate. So where P1, P is equal to H1 rho G and C1 is equal to, these are the formulas already have been proved. So replacing these formulas over here, Q1 minus Q2 is equal to A1 dH1 by dt. The rate at which the liquid leaves the container Q2 enters the equals the rate at which it leaves the wall R1. So P1 minus P2 is equal to R1 Q2. So that gives you the value of Q2 over here. Okay. So the pressure are H1 rho G and H2 rho G. The height will create a pressure. So by replacing the values of P1 and P2, the difference of pressure over here, H1 minus H2 into rho G is equal to R1 Q2. Using the value of Q2 given by this equation, substituting it into the earlier equations, we get this one, Q1 as equal to this. Similarly, for a container 2, a similar set of equations can be derived. Thus, for the capacitor C2, Q2 minus Q3 is equal to C2 dP by dt. We'll be repeating the same steps for the second container as well. And this is the final equation that you will be getting. So this is how you can calculate the flow rate out of the second container, that is in terms of Q3. Okay. Then the third and the last, fourth and the last system building block is our thermal system. So there are only two basic building blocks for thermal system: the resistance and the capacitance. There is a net flow of heat between 2 points if there is a temperature difference. The electrical equivalent of this is that a current I between 2 points if there is a potential difference. So if there is a temperature difference between the 2 points, then there will be a flow of heat. Similarly, in electrical analogy, we can say if there is a potential difference between 2 points, the current flows. So the current over here or the heat over here is equivalent to the current, and the potential difference between the 2 points is equivalent to the temperature difference between the 2 points. So if Q is the rate of flow of heat and T1 minus T2 is the pressure is the temperature difference, then T2 minus T1 upon R is equal to Q. This was again similar to the fluid system, where the P1 minus P2 was equal to R times Q, because over there the pressure difference creates the liquid to flow. Over here the temperature difference creates the heat to flow. So whatever the resistance has been encountered during the journey from one point to the another point, that flow rate of heat will depend upon the resistance. The value of the resistance depends upon the mode of heat transfer. You already know about these things. In the case of solids, we can say that Q is equal to A times K, where A is the cross-sectional area of the material, and you must know this. This is known as the law of thermal conductivity, right? In a solids, and K is known as the thermal conductivity, and hence you can compare this equation with this one, and finally you can find out the resistance to the heat flow. That comes out to be L upon A times K, where K is the thermal conductivity. So now there is another mode of heat transfer which is known as the convection. So for the convection, the formula entirely changes. You already know Q is equal to A times H into T2 minus T1, where what is H? H is the coefficient of heat transfer. So now again, we are comparing this equation, you call it as number 3. We will be comparing this equation with the first equation. So by comparing these two, again we will get a formula for the resistance. This gives you the formula for resistance. Okay. Now we have found the resistance. Now the next step would be to find out the thermal capacitance. It is a measure of the store of internal energy in a system. Thus, if the rate of flow of heat into a system is Q1 and the rate of flow of heat out of the system is Q2, the rate of change of internal energy would be Q1 minus Q2. As increased in internal energy means an increase in temperature, right? Because internal energy is directly proportional to the temperature. So increase in internal energy means there will be an increase in temperature. Since internal energy change would be equal to M into C, specific heat, into change in temperature, whereas M is the mass, C is a specific heat. So rate of change of internal energy would be equal to M into C into rate of change of temperature. You got that? So that means we can compare this equation with the fourth equation. Okay, so from these two, what we'll be getting? Q1 minus Q2, which is the rate of change of internal energy, that will be equal to mass into specific heat into rate of change of temperature. So this equation can be further written as Q1 minus Q2 is equal to C times dt by dt. So what is C? C is the thermal capacitance, so that will be equal to mass into specific heat. So now you have got the two building blocks for the thermal system, that is capacitance and the resistance. The value of resistance for conduction and for convection already have shown to you in the previous equations. Now we have built electrical system, mechanical system, fluid system. Now in this section we will be building up a model for a thermal system. Okay, so consider a thermometer at a temperature T, which has just been inserted into a liquid of temperature TL. If the thermal resistance to heat flow from the liquid to the thermometer is R, okay, then Q is equal to what? TL minus T by R. The amount of temperature difference upon R is equal to Q. Already we have shown that. And you also know that Q1 minus Q2 is equal to C dt by dt. Since there is only a net flow of heat from the liquid to the thermometer, right? So Q1 is equal to Q, but Q2 is equal to 0. Okay. So finally, what we'll be getting? Q is equal to C dt by dt. Dt is the rate of change of flow, rate of change of temperature. Substituting this value of Q in the previous equation, what you will be getting? C dt by the, we'll be using this to this. So C dt by dt is equal to TL minus T upon R. So just by rearranging, we'll be getting this equation. This equation is the first order differential equation, describes how the temperature indicated by the thermometer will vary with time when the thermometer is inserted into a hot liquid. So this is like you get a question in the exam that build a thermal system from a then you can give this example, building up a model for a thermal system. Then you can give this example, but you must remember the elements for that. Now, as we have done for the fluid system, we have used two containers, Q and Q1 and Q2 and Q3. Similarly, over here we have created another thermal system where we have a two temperature differences over here. One is T, another one is T naught. So in the previous system, which we have just seen, there the Q2 was equal to 0, but here the Q2 will be having some amount of value. Okay, so accordingly, Q1 minus Q2 is equal to C dt by dt. This is our prime equation. If the temperature inside the room is T and that outside the room is T naught, then replacing Q2 is equal to T minus T naught by R, where R is the resistivity of the wall. Substituting for Q2, you can get this equation. Okay, so this is another equation for when there is a Q2 system. Q2 exists for your system. So you can have this final system elements. All these have been given in table 17.5. The mathematical, the mechanical, the electrical, the fluid, the thermal. So you must remember these, and